Okay, so this is my website address. So once you go there, you can see a link for the course 228 data structures and algorithms. Okay, and as I said, I'll post everything that we do in the class online. So I'll update the TA information once it is available. As I said, they'll be available from September 1st. Now all the code that we're going to go through. Any question? Okay, so all the code that we are going to go through, I'll be posting in Canvas as a C++ file itself. But in addition to that, I'll also post things in online, the course website. But what I post here will be a PDF file. They are not letting me to post a CPP file. So Canvas is going to have all the CPP files. But I'm just letting you know the code is also going to be available in the website. And it'll also be available in Java. So even though Java is not the language we'll be using in the class, but if someone has a Java background and you want to see how to write all this code in Java, you can refer to this code. Now, so as I said, all assignments and exams will be posted here, and the schedule is also available here. Okay. All right. So let us now get started. Alright, so the first module we are going to focus more on the time complexity analysis. Again, this is going to be only like a very high level overview of time complexity analysis. There is a second course following this course, CSC 323 Algorithm Design and Analysis. The computer science students are required to take that course. The computer engineering students are not required, but they could take it as an elective. So that's going to be kind of like a follow-up course of this course. So in this course, we'll focus more on data structures and how to analyze and basically develop code for their working. And then we'll see how to analyze their algorithms to use the data structures. There's something called algorithm design. Okay, so given a problem, how you come up with an algorithm to solve that problem. And at that time you will use the data structures, you will not design the data structures. So that is the focus of the second course, algorithm design and analysis. So nevertheless, you should know what an algorithm is in this course, so that you could develop some algorithms for the working of the data structures. The following course, you will use this data structures and as part of an algorithm for a larger problem. Alright, so as you proceed in this course, you will understand what are all the things I'm talking about now. Alright. So an algorithm is basically a procedure to solve a problem. And so from a computer science point of view, we should give the instructions to the computer how to solve the problem, and it will solve it for you, as you would have done programming in 118 and 119. Okay, so when I'm lecturing, I'll come back and forth to the screen to see if anyone has questions. So, okay, so now given a problem, you should first come up with an algorithm, which is like the procedure, the logic that you would use to solve the problem, and then you should program it. So you should not program things right away without coming up with an idea. So that means you should be able to represent that logic as a kind of in a code, but not the actual C++ code, but what we'll call as a pseudo code, or some way you should convey your idea. So later, as we proceed in the course, you look at what is the pseudo code for an algorithm. So looking at the pseudo code, you pretty much get the idea of the problem, of the approach you're going to take to solve the problem, and then you program it. So that means you should be able to analyze, looking at the pseudocode and the logic, what will be the time the program will take to run. You're not going to analyze right away the number of seconds or milliseconds the program is going to take. You're going to analyze the time complexity based on the input size. Okay, so that's where the input matters, because no algorithm will run without any. You should have some input that needs to be processed by the algorithm, and you should get the output. Now again, most of the pretty much all the algorithms that we're going to see are going to kind of be unambiguous. There's no random thing that we're going to see in this course. Of course, there are some algorithms later in your career you will see run on a random basis, but what we see in this course is going to be algorithms that are unambiguous in nature. That means for a given input, you should always get the same output. You should not get different output for the same input. That's what I mean by unambiguous. Okay, and the range of input should also be specified. It means if it's integers, what is the range of the integers that should be input, and so on. Now, so the same algorithm can be represented in different ways. That's where things are important to be noted, because the logic could be the same, but how you want to program that logic, you could differ how you are going to implement that logic or the algorithm. Okay, and so that is one algorithm, multiple different possible implementations. Now, one step ahead, you could also have more than one algorithm for the same problem. So later in this course, as well as in the following course, we will look at the sorting problem. For example, given a sequence of integers or list of integers, I want a sorted list of those integers. So the sorting could be done different ways. So you'll see, look at different sorting algorithms, and each of the sorting algorithms could be implemented again in different ways. So you have these two levels. Different algorithms for the same problem, and each algorithm could be implemented differently when it comes to implementation. So in this module, we'll look at how to analyze the time complexity of the algorithms in a theoretical fashion based on the input size. We'll just consider some simple problems. Then as we proceed in this course, we will use this as a basis to get an idea of, if I develop an algorithm for a particular data structure and its operation, how much it will take as a function of input size. And then you will compare that, the theoretical time complexity that you will come up with the real time after you implement. Is it really showing that trend of time complexity? Okay. All right. So typically we'll represent the time an algorithm will take as a function of the input size, which is in general represented as n, the number. So for example, most of the times we'll work with an array or a sequence of data like integers or characters and stuff like that. So we say n is the number of integers, number of characters that we're going to process. Sometimes you may work with a graph or a tree where we're going to have vertices and edges. If you're not familiar with the term yet, don't worry, we're going to see that as a separate module. But you might have seen this in discrete structures. And sometimes instead of a sequence or an array of integers or characters, you may have just a single integer as input. For example, given an integer, you want to decide whether it is prime or not. So in that case, how would you represent the time complexity as a function of the input size? So in that case, you would use log of n, which is the number of bits needed to represent an integer n. Okay. So if, say for example, if the integer is 10, the number of bits that you need to represent 10 is going to be log 10. And it's actually log 10 to the base 2. Okay, so this is the number of bits to represent 10. In binary. Okay. Now that is time complexity, and we're going to see that throughout this course and also in this module in detail. Now we also need to look at or think about space complexity for our algorithms, okay, and the design of the data structures that we come up with. So space complexity, what it means is, given a problem, of course, you're going to have an input. So when you know, like when you write a program, you say the input is an array, you need to allocate space to store that input, the array. So we cannot get around that. We have to allocate space for that. So by space complexity, what I mean is, what is the additional memory that we need to allocate for our program in addition to the input and output? So that's what I always mean by additional memory. So additional memory means in addition to what we allocate for the input and output, how much more we need to allocate for our algorithm or the program to run. Now, if that additional memory that we need to allocate for our program does not grow with the input size. So for example, if I want to sort 10 integers, I need to use, say, some temporary variables that are not part of either input or output, some temporary variables to swap and things like that. So that how many temporary variables do you need to use? If you want to sort 10 integers, let us say use 3 temporary variables. If you want to sort, say, 1 million integers, you still use, say, 3 temporary variables. That means the amount of additional memory that your program needs does not grow with input size, and that's a good thing. Okay, so we say that program requires constant space complexity, and such algorithms are said to be in place. That means if algorithm does not require additional memory that grows with input size or that increases the input size, such algorithms are good and considered to be in place, and they're also said to require constant space complexity. Constant space complexity means it does not grow with input size. Okay, so we can say it is theta of 1 time. We use the notation theta. Okay, so theta of 1 space complexity. On the other hand, if you come up with an algorithm whose space complex requirement grows with input size, so as I said earlier, if I want to sort 10 integers, I need to use 3 temporary variables. If I want to sort 1 million integers, even if it goes to 300 or 3000, that's not good, because the amount of additional memory that you need proportionally grows with input size. That's not good design of an algorithm, but still okay if that's the only way you can solve the problem. Okay, so you should remember this thing about space complexity, and always when you are designing an algorithm to design the function of a data structure, you should try your best to design a constant space complexity algorithm. Only if it's not possible, then you can go for something that grows with input size. Okay. Alright, so let me stop this video for a second and